Hello audience. Today we will discuss about the different topologies used in DC to DC converters. A DC to DC converter takes the voltage from a DC source and converts the voltage of supply into another DC voltage level. They are used to increase or decrease the voltage level. This is commonly used in automobiles, portable chargers and portable DVD players. Types of DC to DC converters. There are mainly two types of DC to DC converters. DC to DC converters without isolation. These DC to DC converters does not have any isolation transformer between input and output stages. Non-isolated converters are used when the change in the voltage is small. The input and output terminals share a common ground in this circuit. The following are the different types of converters in this group. Buck converter, boost converter, buck boost converter, step down, buck converter. A step down circuit is used to generate a lower voltage than the input. It is also called a buck. The polarities are the same as in the input. Step up, boost converter. A step up circuit is used to generate a higher voltage than the input voltage. It is called as a boost. The polarities are same as in the input. Buck boost converter. In buck boost converter, the output voltage can be increased or decreased than the input voltage. It works to either boosting or bucking the voltage. The common usage of this converter is to reverse the polarity. Charge pump. This converter is used to step the voltage up or down in applications that have low power. The disadvantage of non-isolated is cannot give protection from high electrical voltages and has more noise. DC to DC converters with isolation. A transformer is provided in between to isolate the input and output stages. Some of the commonly used DC to DC converters with isolation are flyback converter, forward converter, push-pull converter, half-bridge converter. Let's discuss about the isolated converters. These converters have a separation between input and output terminals. They have high isolation voltage properties. They can block the noise and interference. This allows them to produce a cleaner DC source. Flyback converter. This converter works similar to the buck-boost converter of the non-isolating category. The difference is it uses a transformer to store energy instead of an inductor. Flyback converter is the most commonly used SMPS circuit for low output power applications where the output voltage needs to be isolated from the input main supply. The output power of flyback type SMPS circuits may vary from few watts to less than 100 watts. The overall circuit topology of this converter is considerably simpler than other SMPS circuits. Input to the circuit is generally unregulated DC voltage obtained by rectifying the utility AC voltage followed by a simple capacitor filter. The circuit can offer single or multiple isolated output voltages and can operate over a wide range of input voltage variation. In respect of energy efficiency, flyback power supplies are inferior to many other SMPS circuits, but its simple topology and low cost makes it popular in low output power range. The commonly used flyback converter requires a single controllable switch like MOSFET, and the usual switching frequency is in the range of 100 kHz. A two-switch topology exists that offers better energy efficiency and less voltage stress across the switches but costs more and the circuit complexity also increases slightly. In case multiple isolated output voltages are required, the flyback transformer will need to have multiple secondary windings. Each of these secondary winding voltages are rectified and filtered separately. Forward converter. Forward converter is another popular switched mode power supply, SMPS, circuit that is used for producing isolated and controlled DC voltage from the unregulated DC input supply. As in the case of flyback converter, the input DC supply is often derived after rectifying, and little filtering, of the utility AC voltage. The forward converter, when compared with the flyback circuit, is generally more energy efficient and is used for applications requiring little higher power output, in the range of 100 watts to 200 watts. However, the circuit topology, especially the output filtering circuit, is not as simple as in the flyback converter. The basic topology of the forward converter. It consists of a fast switching device along with its control circuitry, a transformer with its primary winding connected in series with switch to the input supply, and a rectification and filtering circuit for the transformer secondary winding. The load is connected across the rectified output of the transformer secondary. The transformer used in the forward converter is desired to be an ideal transformer with no leakage fluxes, zero magnetizing current and no losses. In fact, due to the presence of finite magnetizing current in a practical transformer, a tertiary winding need to be introduced in the transformer and the circuit topology changes slightly. Push-pull converter. The push-pull topology is essentially a forward converter with two primary windings used to create a dual drive winding. This utilizes the core of the transformer much more efficiently than the flyback or the forward converters. On the other hand, only half the copper is being used at a time, thereby increasing the copper losses significantly in a similar size transformer. For similar power levels, the push-pull converter will have smaller filters compared to the forward converter. However, the advantage that push-pull converters have over flyback and forward converters is that they can be scaled up to higher powers. Switching control can be difficult with push-pull converters, because care has to be taken not to turn on both switches at the same time. Doing so will cause the equal and opposite flux in the transformer, resulting in a low impedance and a very large shoot-through current through the switch, potentially destroying it. The other disadvantage to the push-pull topology is that the switch stresses are very high, twice of input voltage, which makes the topology undesirable for 250 volt AC and power factor correction applications. Half-bridge converter. The half-bridge topology, like push-pull topologies, can be scaled up well to higher power levels and is based on the forward converter topology. This topology also has the same issue of the shoot-through current, if both switches are on at the same time. In order to control this, there needs to be a dead time between the on times of each switch. This limits the duty cycle to about 45%. Beneficially, the half-bridge topology switching stresses are equal to the input voltage and make it much more suited to 250 volt AC and power factor correction applications. On the other side, the output currents are much higher than the push-pull topology, thereby making it less suited for high current outputs. In the figure, you can see comparison of different topologies. Thanking you.